What I want to do is take you all the way down to the terminus region of the Athabasca River, to the Peace-Athabasca Delta, where we've used these one-way time machines to go back, select sites that have integrated material that has come from either the atmosphere or the Athabasca River waters from pre-industrial time, to use that as a good baseline, a reference against which to compare for evidence of pollution. Try to give you a bit of my rationale here. A lot of this you've heard before, but sediment quality for aquatic ecosystems, monitoring of contaminants, sediment quality monitoring is really widely used around the world. Many of the contaminants of concerns, the metals, the organics, don't tend to dissolve well in water. They have an affinity for the particles, so that's where they tend to be. A lot of the organisms encounter those contaminants by interacting with the sediment, so that's where a lot of biotic effects come. And we've heard time and time again around the oil sands, the real challenges are that, like in many other places, mining activities, industrial activities tend to be located very close to where natural sources of those contaminants are. And unfortunately, we start to monitoring after the fact, after we start to get concerned about the activities that have preceded. And this is certainly the case for the oil sands region. The black here being the footprint of mines in 2009, a handy map that I had. It's of course different now, but the mines are located exactly where the bitumen layer, the McMurray Formation, is within 75 meters of the surface. And there's about 100 river kilometers along here where that bitumen layer comes right out in the river bank and long has known to naturally erode. So when you do comparisons upstream versus downstream, and you find higher concentrations downstream, some of that might be due to the industry, but some of it is also due to the natural resource, and disentangling the two is pretty tricky if you haven't measured upstream and downstream before the industry. And of course, our sort of integrated, I learned about some other monitoring that goes on, but the key one that began, RAMP, and its successors began 30 years after the mining industry began, and so it's pretty tricky to sort that out, and that's a lot of the dilemma that we all deal with. So trying to disentangle what this is contributing to the river and the air compared to these sorts of natural deposits that come down is a real challenge, and for monitoring programs it's really tricky to disentangle. You're left with looking for trends over time in a river where flow volumes change quite a bit, and a lot of this material will get picked up in the spring when the river levels rise with the snowmelt input, and the ice scours that stuff and brings it down. And that's a time when monitoring programs are challenged to take any kind of measurements for safety concerns, for equipment working, and so on. A lot of the concerns, we ended up working in the Peace-Athabasca Delta on contaminants because that's where a lot of the concerns tend to pop up. I mean, certainly Fort McMurray, I understand that. We've heard a lot about that today. But the Peace-Athabasca Delta is where the Athabasca River ends. Its flow slows down, the sediments are dropped and build up a floodplain. And so whatever the river has caught, natural or anthropogenic, gets put there. There's a town of, I think, roughly 1,000 residents, mainly Aboriginal, First Nations people who utilize that delta, very concerned about the changes that it might be for their health. They're afraid now, I think, to drink the water, concerned about effects on the biota they eat, and so on. And so this is what drove us to work there. This delta is, the Athabasca Delta is building up, a river is building up a delta as it drops its sediment. In fact, that area has been rising so much that the flow is now starting to come through this way. There's the Peace River, hundreds of lakes, over 1,000 small lakes and things here that span a range of hydrological conditions. And some of that complexity has, I think, steered people away from doing monitoring in here because there's two rivers and potential sources, finding lakes that represent what the river is carrying and so on. It can be challenging, but we happened to be doing research there for about a decade before we started looking at contaminants, assessing hydrologic change in context of a dam on the Peace River. And once you get to understand the hydrologic complexity, you can use that to your advantage to choose carefully the sites to look at to answer the questions that are of concern. And I hope I can show you how we've done that. So what I'm going to try and show you is work. I'm going to follow this sediment work with a little bit of introduction to some monitoring we're doing, but I'm going to focus most of my scientific presentation here on how we've teased out information from lake sediment cores to determine pre-industrial baseline or reference levels for metals and pHs, and assess to what extent atmosphere has been an important vector and whether there's evidence that has increased since onset of oil sands industry, and to look at the role of the Athabasca River in depositing metals and pHs, and is there any evidence that it's increased. So I'm going to take you to 3 lakes. This was a project that ended up being funded by Suncor after we went to NSERC and they told us this was in industry's interest and industry should pay. So we were directed to get industrial funding, and Suncor stepped up. These were sites where we had previously collected sediment cores to reconstruct the hydroecological changes in the delta. And so we knew that these 2 lakes have flooded in the past, including pre-industrial times, and provided an ability to get some information about what the river is carrying in terms of contaminant load, and one site that has continued to be quite flood prone since the onset of oil sands, so we could compare pre and post, and I'll show you that. I'm going to start by showing you this lake, pad 18. This is a little bit like the lakes that Colin looks at. It's got a very small catchment area. It's perched high in that landscape, and we know that all the water that's in that lake comes from precipitation that falls to its lake surface or to its small catchment that is not developed at all. I think scientists are about the only people that visit this lake. It's far away from the rivers and elevated. So I'm going to start by showing you this core spanned from about 1750 to 2010 when we collected it. I've got 4 metals plotted here. And what I'm expressing here is what we call the adjusted excess flux. So you can interpret this as, this is the flux of each of these metals, lead on top that I'll show, but the other patterns are comparable in many ways. The flux rate of these metals to the sediments above a pre-1900 average. Okay, so anything that comes above 0 is an additional source from pollution. And so what we see is a pretty interesting pattern that you'll find just about anywhere in the northern hemisphere. Lead rising around 1920s, peaking in the late 60s, and then when we took lead out of fossil fuels and coming crashing down. You can see strong correlation with the total Canadian atmospheric inventory from industrial emissions, this thick black line coming down, and negatively correlated with bitumen production. So that actually, clear evidence that the oil sands has not led to air pollution of metals to that region. Other metals showing similar patterns. So in the interest of time, I'll focus on the story about the river. So we have these 2 lakes, pad 31 and pad 23, down in the Athabasca sector along the Athabasca River and distributaries. And when we had cored these lakes, we realized that back in the bottom of these lakes were flooding frequently back in the past, and that they contain sediment that came from the Athabasca River, and we could use that to characterize pollution levels. Now, when it comes to, I'm going to show you metal data first and then some pH data. And to interpret metal data, we need to account for variations in sediment grain size that I think Colin showed us normalizing to aluminum. I'm going to normalize to lithium. But this is a slide to just try and illustrate for anyone who has trouble with that concept, the reason why we do that. So pad 31, the local name is Johnny Cabin Pond, so it's the same lake, even though I give it a different name here. I happened to sample it in spring of 2007, just days after an ice jam flood brought floodwaters in there, and we had to tramps through really thick river sediment that had been deposited on our path from the river to the lake. Now you would imagine this is the same event, deposited this material. I grabbed 3 samples and put them in bags thinking that somehow this is going to be interesting scientifically, and one was on the levee, one about halfway through the woods, and one by the lake margin. And so it was carrying a contaminant load from the river at the same time, in that flood event. And so you expect a metal concentration to be fairly similar, but in fact, at those 3 spots, the concentration of vanadium, a metal of concern from bitumen, was twice as high at the lake edge than on the levee. And the reason is that they differ in grain size. The coarse stuff at high flow drops out first, and the fine stuff goes in, and the finest stuff goes into the lake. So the highest concentrations hit those aquatic systems in the lakes. And so the way that we try to, we're not interested in that kind of signal in interpreting metal concentrations. And when you're looking at sediment cores through time, and past flooding events that bring material into those lakes could vary in intensity and grain size, you don't want to be interpreting concentration changes just due to that. You want to see beyond that. So many people use aluminum, and Colin showed plots normalized to aluminum. We used lithium. It gave us the strongest correlations. And when we plot pre-1920s sediment that was from the river in the lake, it follows along one source, along the line, showing a straight line showing one source. And if we then plot those three measurements, they also plot along that source, along that line, indicating a similar source of that material, of that metal. So what we think we've done is we've been able to create normalized these sort of vanadium, lithium, and other metals. I'm just going to show you vanadium, but we've done this for a suite of other metals. We can interpret this. We've got the linear relation between vanadium and lithium for all of the samples in our sediment cores pre-1920, before there's any signature of elevated levels from atmosphere. And we've got 95% confidence intervals. And so now you can interpret that if you were to now find more than 2.5% of your samples above that upper 95% confidence interval, is evidence of a new source of enriched vanadium that could be due to pollution. And if it's below that, then there's no evidence of pollution. And what we did is we went to the publicly available RAMP data. They actually were sampling 6 different sites within of river bottom sediment in the tributaries in the Athabasca Delta. And between 2010 and 2013, they sent their sediment to the same lab and used the same analytical method that we were using on our sediment core. So we could then put that on this pre-industrial baseline and assess for evidence of pollution. And you can see that all those measurements by RAMP fall within the 95% confidence interval, suggesting no evidence of pollution of the recently deposited sediment at the top of the bottom sediment in the Athabasca River. What we think might be a better expression of the data for managers is to take the vertical offset from this line, which we call residual vanadium, essentially takes that line and turns it horizontal, and then we can plot by time. And now, as monitoring data builds up, collects these samples and continues to measure them, we can look for time trends of increase or whatever. So there's some ability to detect temporal trends through this method. One thing that we've done in the last 2 years is we've added a few more measurements. We've taken sediment cores from 2 more flood-prone lakes, one out on Athabasca Chippewa First Nation land outside Wood Buffalo National Park, another one along the Ombra River. And we've placed them on this same relation, and all the data points fall within that 95% confidence interval. So again, no time since the bottom of those cores in the 1940s is there evidence of elevation of vanadium above pre-industrial baseline. And we collected surface sediment from a network of 60 lakes spanning the full hydrologic gradient, from lakes that are continuously flooded by the Athabasca River to other ones not very often. And they also fall within that range of pre-industrial baseline. So no evidence of pollution from what we can detect. Just going to quickly show you evidence of PACs. Now what we did is we identified a subset of PACs that tend to be elevated in sediments in these lakes during periods when we can identify that floodwaters provided that sediment compared to when they're not flooded. And these seven PACs are abundant in bitumen, make up about 50% of the PACs that are in the oil sands, the McMurray formation. Pad 31 was flood prone from 1700 to 1940. There was a short period where it wasn't flood prone, and then after 1982, a channel connected and routes floodwaters to this lake. And so we were able to compare pre-oil sands versus post-oil sands, and also put it in context of this flood deposit that I collected in 2007. So you can see, relatively higher levels when the lake was flooding, during the 2 periods when it was flooding, and went down when it wasn't flooding, except for 1965 and 74 when the lake flooded. We then used an independent samples t-test to compare if the average concentrations differ between pre and post oil sands, and we got a not significant value, so no evidence of a change in concentration of these river-transported bitumen-associated PACs, and led us to the conclusion that natural erosion of bitumen deposits along the Athabasca River and its distributaries continues to be the main source of these contaminants. So I've got a few take-home messages in a little segment after this, but certainly sediment quality monitoring, commonly used and effective way of tracking river pollution. Abilities to monitor for and determine industrial impacts has been hampered by inability to determine pre-industrial baseline. Floodplain lakes contain that information. If we go and carefully select the sites, we can tease out for evidence of pollution. And of course, we all recognize that the industry is continuing to grow, expand northwards, and so on, come closer to that delta. And so, in our view, it's probably prudent to develop a good monitoring network for that delta. And in this regard, we've been able to, with NSERC CRD funds and money from industrial partners, been able to begin some research to underpin a monitoring program. And the concept is that we have developed ways of tracking hydrology, contaminants, biology, toxicity through very easily used equipment, rapid sampling at each site, where the use of this equipment would require minimal training from people in agencies or local First Nation community-based monitoring programs. And I'm just going to tell you a little bit about it. We designed this based on, and we've been working in this delta for 16 years, and certainly have heard about concerns. So we want to be able to track concerns around pollution and water consumption from the oil sands, but there's also huge issues around the effects of hydro dams on water levels and flood frequency, as well as, of course, the interaction of climate change and declining headwater supplies of water on that delta. And these have really come to a head recently with a petition by the Mikisew Cree First Nation, where they petitioned to the UNESCO World Heritage Committee to change the status of Wood Buffalo National Park to in danger for several reasons. Two I've highlighted here that are about the release of contaminants from oil sands, as well as effects of hydrologic change on the rivers that feed that delta. And so we wanted to design something that could get at all of those interactions. So we're collecting samples to track hydrology, the sources of water, map out flooding, extent of evaporation, fluctuations in water levels, how that influences water chemistry and biota, lake conditions, and how the interactions of those things affect the distribution and hotspots of contaminants, and assessing sediment for toxicity to biota as needed for adequate risk assessment. And we've been collecting water samples 4 times through the open water season to track hydrology and water chemistry. We deploy samplers for 1 month to track contaminant levels and other aspects of longer-term perspectives on hydrology and ecology. And we collect periodically surface sediment to map out the distributions of metals, pHs, and assess for toxicity. And we've been trying to work with local agencies and monitoring programs so that this can move forward in the future. And just to give you a sense of the scale of this, we have a network of 60 lake sites and 10 river sites that span the Athabasca and Peace sectors of the Delta and in between. About half of these lakes flooded with the last major ice jam flood, and some of them are sites where local First Nations, Parks Canada collaboration assesses muskrat health and numbers, and so we're trying to make sure that the monitoring gets added value by being coordinated with other places.
Skimmon from Vernon, BC. I notice you haven't taken any cores, or have you thought of taking cores from Lake Athabasca, which would be the ultimate deposition zone. You know, the delta is flushed through regularly. These lakes that are flooded, it's very episodic. It may not be at a time when the river is contaminated, but if you went into the lake itself, where the sediments would ultimately settle and stay, you might find different results. I wonder if you've thought of that.
Yeah. Okay, so that's a good question. It is one that we've thought a lot about. And it is, I think, instinctive or intuitive to think about going at some distance off the delta front as a place where, of course, all the material is being deposited. But there's a few reasons that have hampered us from doing that, or that have caused us to consider not doing that yet. And a main one is that the distributary channels switch their direction over time. It's not always a constant flow out one point. And so you would get different answers, in taking cores a few hundred meters apart. The sedimentation rates are very rapid, to my understanding, probably so rapid that our methods that allow us to date the different levels in the sediment core become quite limited. So those are some of the main reasons why we haven't gone there, is that we haven't thought that we could actually, find 1 or 2 or 3 locations that would give us a definitive record. We've much preferred to go to these shallow lakes that are regularly, quite regularly getting floods, at least regularly enough for our purposes to track these patterns over time.
Maybe I might just comment on that, Brenda, because I was involved in a little bit of work that did work on Lake Athabasca, and I know one of the challenges of getting good sediment cores from that lake is that there's a lot of mixing of the bottom sediment because it's so shallow, and to date the sediment core, you need those sediments to remain in place once they've settled to the bottom. And if they get mixed, then you can't build a reliable age depth model because you've basically mixed up the whole column. And so that's one of the real challenges, but I know Marlene Evans has been working on that a little bit. I think she just published a paper on that, but sorry, Roland.
No, that's right, yeah.
Hi, Roland. Nice talk. I'm over here.
Oh, yeah.
I'm Tim Archuszewski from COSIA. I just have a couple of questions / comments about the 95% prediction intervals that you used.
Okay.
So one of the, for lithium and vanadium, so one of the things was, and it was something that you mentioned, is that 2.5% of your observations should be above that trigger. And it looked like in the graph that you had the most observations that wasn't happening. So maybe I just missed that, but that would certainly be something that would catch my attention, that you're not seeing something that you should. And the other thing would be, one of the things that we're trying to do is back away, not entirely, but one of the problems with those tails of the distributions is that they're typically very difficult to estimate. So one of the things we're doing is we're trying to move away from those tails and use things like medians or 75th percentiles. Yeah, this one here. So 2.5% of those observations should be above that upper, the dash dot dash line.
Yeah, that's right. Yeah, let me clarify one thing. I think sometimes when I'm speaking, my brain's ahead of me. They're 95% prediction intervals. Yeah, not confidence intervals. So they're for individual measurements. So 95. You're right. 95% of the values should fall within.
Yeah.
In the long run. Yeah.
Yes. Yeah. That's a very excellent.
That's right.
That's an excellent point.
Yeah, there would be nothing unusual about 2.5% of those data points falling above that line.
Yeah.
And you can see too that, yeah, I mean, there's more detail in this graph than I can put in a 15-minute
Sure.
talk, but here's the prediction interval, and we straightened it out to get around
Yep.
that flare,
Right.
and we were using the straightened line as
Yeah.
the basis of our interpretation.
So one of the things that I would do would be to look at something like that regression line, because at least half of your data should be on or above that regression line. So it's just a way to check, because the percentiles are often estimated with some variability or some uncertainty. It's
Right.
just a way to check,
Yep.
Okay. Is this single trigger actually telling me the complete picture? There's nothing wrong with what you've
Okay.
done. It's just, a comment.